Good morning, everybody. My name is Juan Felipe. We are Group 7 and we are going to present the design and simulation of a centrifugal pump for its operation with water and mineral oil. In order to understand the development of the project, we are going to start talking about turbomachines, materials and methods, obtained results, and the proper analysis, comparing them with the manufacturer's data. Introduction. Turbomachines are devices used to provide or extract energy from a fluid. Among the most known turbomachines we found, centrifugal pumps, whose main functions are to move a fluid through a system and compensate energy losses caused by friction with pipes, accessories, and other factors. These machines are very important in many industries like petrochemistry, pharmaceutical, and food ones. According to USA Department of Energy, pumping systems represent 20% of the world electrical energy demand. This is one of the reasons why an efficient prediction of the pump's performance is accomplished in order to achieve optimal operations and cost-effective designs. Design. The pump design was done in Autodesk Inventor 2020, based on the calculations for a 1D design. The following planes show the main dimensions and characteristics of both the impeller and the diffuser. Several restrictions were considered, like the diameters of suction and discharge, the side clearance and the blade thickness. It can be seen as well that the pump has 6 blades.
So, in order to study the system performance, there are some assumptions made. In this case, the assumptions are the following. In the first place, it was assumed that there is no mass accumulation inside the pump and all state variables are constant over time. So, steady state was assumed. Chosen fluid was liquid because we are working with water and mineral oil at operation conditions in which they are still liquids. On the other hand, the segregated flow model was selected because we assumed that the fluid is incompressible, and this could help optimize the simulation time. Constant density is assumed because we are not interested in the effect of temperature on viscosity or density. Finally, the turbulent flow was considered based on the Reynolds number for each fluid. We can see here the value for water and oil. Reynolds average turbulence was selected too. This model has three components: K epsilon turbulence, realizable K epsilon two-layer, and two-layer all-white plus wall treatment. This model provides a solution for two variables: turbulence kinetic energy and rate of dissipation of turbulence kinetic energy. For the generated mesh, a steady and turbulent flow was assumed for both incompressible fluids. The inlet and outlet of the pump were set as mass flow inlet and outlet, and interfaces were established at the upstream and over the rotating zone. For the mesh, polyhedral measure was used and prismatic layers were included. Surface remeasure was used and custom controls were created over the blades, the blade tips, the hub, and the top of the impeller. With the previous considerations and the parameters shown in the table, the following mesh was generated with a total of approximately 1 million cells. The planes that cut the pump were created for the proper analysis of fluid before entering the pump and after getting out of it. So, as you can see in the table, we set the base size of 2 millimeters, and on the surface control parameters, we have the target surface size of 0.5 millimeters and the number of Prim's layers of 4. A mesh independency test was carried out in order to determine the optimal number of cells for the simulation. And three different mesh sizes were evaluated: the coarse mesh, the base mesh with reference value, and the fine mesh. The variable setting was the base size with values at plus minus 30% of the base size set for the reference mesh, in this case of 2 millimeters. As you can see in the figure, the number of cells is proportional to the computational cost, where the base mesh takes twice the computational time in comparison to the coarse one, but there is a significant drop in the waterhead error, from 4.8% from the coarse mesh to 2.1% from the base mesh. The differences between the fine and base mesh are less significant. Based on this, independency was confirmed and the base mesh was chosen for the following simulations.
The curves shown here correspond to the simulation results and their comparison with the curves reported by the manufacturer. We can see that the efficiency data is more adjusted to the theoretical curve for the mineral oil, compared with the behavioral efficiency curve for water. Besides that, the total head values for water are higher than those for mineral oil, a behavior associated to the fluid's viscosity. Resistance to movement is greater for oil than for water, which can also be understood as an inverse relationship between the fluid's viscosity and the properties analyzed here. A ramp decrease can be seen between the first two head values for water, which can happen due to losses by friction or the highly turbulent flow. In general, behavior different from the ideal may be attributed to mesh limitations, geometry construction, and assumed simplifications in models and physics. As you can see in the figure, the worldwide plasticines were presented for water and mineral oil at the best efficiency point. The color bar indicates that most of the impeller Y plus values are less than 5 for both cases, but there are some regions along the upper edge of the impeller that have greater values. This happens due to the absence of prismatic layers in these parts, and it can be associated with the multiple surface controls that were set in some regions, in a way that a detailed definition of the mesh may be lost in some parts. In addition, another possible cause of this condition is the hierarchy that the program software follows for mesh generation, considering the surface control set by the user, which may cause the loss of conditions in some regions. Here we can see the velocity profile for mineral oil and water. As it can be seen, there is an increase in velocity magnitude as the liquid moves from the impeller through the diffuser, and it decreases when it reaches the outlet zone. The maximum speed is obtained at the external blade tips. A possible reason for the velocity decrease at the outlet could be that the fluid crashes with the pump walls and it suddenly slows down. The impeller velocity profile is not shown because there are no changes between both liquids and the angular velocity in both cases is the same. It is important to mention that for turbulent regimes, inertial forces are more dominant than the viscous forces.
We are going to talk about the pressure. The main function of a centrifugal pump is to increase the pressure of the fluid, and this is done by accelerating fluid particles and then deaccelerating them by crushing the fluid particles with the pump walls. So, the efficiency of the pressure increase depends on the efficiency of the impeller, velocity, and energy losses can be attributed to the friction force in the system. Here, we can see the absolute pressure profiles for both water and mineral oil. It can be noticed that the outlet pressure is higher than the inlet pressure for both liquids, so the design pump successfully accomplished its function. And now we are going to talk about cavitation. Cavitation is a phenomenon that occurs when the pressure is below the fluid vapor pressure. When this happens, some bubbles are generated and they implode for the surface of the pump. So, for water and mineral oils at 20 Celsius degrees, the vapor pressure values are 2,340 pascal and 20 pascals, respectively. As we can see, the absolute pressure profiles of the impeller, it seems that there are no regions in which the absolute total pressure is lower than the vapor pressure of the fluids. However, deeper analysis over the impeller shows that on the inner tips of the blades there are some points in which the pressure is lower the vapor pressure of the fluid. In this way, cavitation occurs for both water and mineral oil fluids. Now we have some conclusions about the project. The first one is a centrifugal pump was designed and its operation was simulated for water and mineral oils based on the calculations for a 1D design. A mesh with more than 1 million cells was obtained and surface controls were generated over important regions of the impeller, the diffusers, and interfaces. While G plus values smaller than 5 were obtained except over the upper edge of the impeller, which is associated to the absence of the prismatic layer over this area. Curves operation shows the expected results. A higher head for water related to the fluids resistant to the movement to the highly turbulent flows. Velocity magnitude for water is higher than for oil, and it's the opposite for pressure. This is caused by viscosity and its relationship with these parameters. And finally, cavitation was observed over the inner tips of the blades related to the rapid acceleration of the fluid over a submersion zone.